All right, guys, this is the second half of our structural member properties video on civil engineering, and today we're going to talk about modulus elasticity. So this goes with what we talked about earlier when we were talking about the moment of inertia. We remember moment of inertia was all about the geometry of the shape. Modulus elasticity is really looking at the actual material that the shape or the beam is made of. So that's going to be a little bit different. And so when we talk about modulus elasticity, the symbol we use for that is E, and it is really looking at the ratio of stress and strain. So we'll talk about what stress and strain are here in a little bit. But it is a measure of basically the stiffness of a material as opposed to just the shape of it. So you kind of put this together with your modulus elasticity and your moment of inertia to kind of get an overall picture of how stiff or how resistant to bending an object is going to be. Just like we saw with the moment of inertia, the larger the modulus elasticity is, the more likely it is to resist deformation. So if you have a small value for both things, then you're going to have something that's very flexible. If they are both pretty large values, then you're going to have something that's quite a bit stiffer and less likely to bend. All right, so we're going to go back to our beams that we're looking at earlier, but we're going to change one of them. So now orientation is going to be the same for both, but one of these is going to be made of plastic, the other one's made of wood. And so this Douglas fir beam A is exactly the same we're looking at with the earlier video. B is a little bit different because now we're looking at an ABS plastic beam. Dimensionally, they're the same. So they have the same 2x6 dimensions, which again is not actually 2x6. It's 1.5 by 5.5 for the width and the height. Cross-sectional areas will be the same. And then over here, we're looking at I. I is our moment of inertia. And we notice that for this particular setup, the moment of inertia is going to be the same for both. So geometrically speaking, these are both going to have the same resistance to deformation geometrically. So it doesn't really matter which one we look at. From a geometry standpoint, they're both going to withstand bending the same. So the only difference between these two really is the actual chemical makeup of the two materials. And so when we look at that, we said, we know one of them is going to be plastic, one of them is wood. So that's going to be the main difference between the two. And so again, we're going to look at what do we know about these two materials. Obviously, we tend to build out of wood more often than we do plastic. And the reason for that is the modulus elasticity for most woods, not all of them, but for most woods is quite a bit higher than it would be for an ABS plastic. And so if we were comparing these two beams, you really just from experience expect probably B to be the more flexible of the two between A and B. If I had a very large plastic beam, I would expect it to have some flex to it. Certainly a lot more flex than I'd get from a wooden beam. And so if you look at the way they're showing this here, again, this is greatly exaggerated, but just kind of showing the stress testing of these two beams, that you see that B is going to have a much greater deformation. And again, it's not going to be that much. Again, they overemphasize the flexibility of that, but it does show you that B is going to flex more than A would. And so we want to look at kind of how do we figure out how much difference there's going to be, and how do we know which one's going to be the more likely to deform. And so we're going to look at how do you calculate modulus elasticity, and what does that represent in terms of our beam deformation. And so we're going to look at our measure that we're going to look at, and that's the delta max. And delta max is basically how much deflection do we get. So if I'm putting a force on that beam, how much does it bend? How much does it change position as we bend it? And so we'll have an applied force that we're putting onto that. We're going to have to know something about the length of the span between supports. So if I'm putting this up between two ends and kind of using it like a bridge, how far is it between those two end points? How far is it from end to end is usually what we're going to look at. We'll have to know something about modulus elasticity, or we're going to be looking for that. Depends on what we know for this particular material. And then we also need to know moment of inertia, because moment of inertia, while it is a separate measurement, it is going to help us to find the modulus elasticity, or help us to figure out how much deformation we're going to get. So knowing the modulus elasticity is going to be somewhat dependent on knowing the moment of inertia. All right, so here's the formula that we're looking at, and this is for calculating beam deflection. If we were in class, we would actually do a beam deflection experiment, and you could try this at home if you wanted to. You just have to be a little bit careful and keeping your balance. But what we would have done is we would have taken a 2x6 or a 2x4 and set it up between two endpoints, and then had somebody stand on it, and we'd actually measure this deflection and measure how much the beam moves. Since we can't do that together as a class, what we're going to do is just kind of talk about it here. And then again, if you wanted to try that on your own, you could. So what we'd be looking at here is several different things. One of them is that to calculate that deflection, again, that's how far down is this going to bend? You know, how far from its original resting position does it go down whenever you put that force on there? We need to know the force. We need to know the distance from one end support to the other end support. We also need to know the modulus elasticity, and we need to know the moment of inertia. All those things are necessary pieces. So there's like 4 pieces of information we need if we want to calculate deflection. Now, what we would probably be doing is kind of working backwards, and we'd be looking at how do you calculate modulus elasticity. So we would actually solve this equation for E, and then do some measurements. We can measure all these things, measure the force, we can measure the deflection, we can measure the actual dimensions of our board to calculate moment of inertia. And so then we could maybe work backwards and calculate what the modulus elasticity for this would be. What they're telling us for this particular problem is that the modulus elasticity for Douglas fir is 1,800,000 psi, that's pounds per square inch. And then the same dimensioned piece that we were looking at for ABS plastic has a modulus elasticity of 419,000 psi. So you can tell there's a very big difference between those two numbers. Everything else is the same. The length is going to be 8 feet. The moment of inertia is 20.8 inches to the fourth. Our force is going to be the same for both. So the only difference between these two is that modulus elasticity. Again, that's related to the actual material that we're working with. All right, so let's take a look at how that deflection will change. One of the things we'll run into is that when we start doing these measurements, these calculations, we do have to pay attention to units. And so when we look at this, moment of inertia is in inches. This is pounds per square inch, so that's also in inches and pounds. And then our force is in pounds. So we've got pounds and we have inches as our units, except for our length. So our length is 8 feet. That is going to need to be converted into inches. So that's going to be one of the first things we need to do is convert that length. Okay, so we're going to do this first for beam A, which is the wooden one made of Douglas fir. So we look at our force was 250 pounds. That was, again, we got directly from our equation down here, or from our data down here in this table. And then our length we said was 8 feet. And so again, we have to convert that into inches. So 8 feet is 96 inches. That's 8 times 12. And so we're going to do the length cubed. So we're going to get 96 inches cubed. And then down here in the denominator, we have 48. That's just a constant as part of the formula. And again, we're not going to worry about where that comes from right now because that's beyond the scope of what we know how to do mathematically. But then we plug in our modulus elasticity, which is 1.8 million. So 1,800,000 psi. And then our moment of inertia is 20.8. Unit-wise, when we get done, everything should cancel except for one of these inches. I've got inches cubed up here. I've got inches to the fourth down there. Pounds will cancel. So anyway, when I get done with all of these things, what should end up happening is I should end up with a measurement of inches. And you can go through and look at the fraction and kind of deal with the unit cancellation to get to that point. But once we're done, everything's going to cancel. The pounds are going to cancel. All the inches will cancel except for one of them. And so our final measurement here is going to be in inches. And so if we multiply that out, in this case, we get 0.12 inches. That is how much this beam is going to deflect. And so if you think about, well, how much is that? That's about 1/8 of an inch. So not very much. It does have a little bit of deflection, but you probably wouldn't notice it too much. You might feel a little bit of flexing, but not much. It's going to feel pretty solid. If we come back and do the same thing for the ABS plastic beam, you're going to find that this one's a little different because our modulus elasticity is way smaller. And so with that modulus elasticity being in the denominator, the larger it is, the smaller this deflection is going to be. Just knowing what we know about math, the larger the denominator, the smaller the fraction will end up being. And so if I make this E smaller, which is what's happening here with our ABS plastic, we had 1.8 million back here with the Douglas fir. Now we've got 419,000. That's quite a bit smaller. So if I go ahead and plug those numbers in, everything's the same except for this one number. And that's going to make my denominator a lot smaller, which makes the overall fraction, this calculation we're going to do, is going to be a larger value. And so when we divide that, we're going to get 0.53 inches. So we've gone from about 1/8 of an inch up to about a 1/2 inch, a little bit more than a 1/2 inch of deflection. So it's going to bend a lot more. Definitely going to notice that. And so if you're building, say, a house or something like that, having a 1/2 inch deflection in your flooring as you're building is not going to be something that you want. You don't want people walking across the floor and the floor sinking down a 1/2 inch every time you take a step. So one of the reasons we don't build with plastic, there's a lot of reasons why we don't build with plastic, but one of those reasons is it's not structurally sound enough to make you feel comfortable, walking on a floor that's built out of that type of material. Okay, so again, just kind of a quick comparison of those two things. And you're going to get a lot more flex, a lot more deflection with the ABS plastic because it does have a much smaller modulus elasticity. All right, guys, that is the end of that. We will talk a little bit more about how we're going to use that later, but that's going to end off this video right there. Thank you.